All right, so hello again. This is our class number 19. We're going to go over the Python part of our decision trees algorithm, classification and regression. So for classification, I chose the data set that we're all familiar with. The data set is called social network advertisement. And as a quick reminder, just let me actually run through them. Look at the head of the data set. You want to see if at the end of the day, someone purchased an SUV or not by looking at their estimated salary, their age, and their gender, right? So this is a very simple data set. And let's see how we can use decision tree classification for that. We can look at the balance of the data, relatively balanced, 65-35. So I'm not concerned when it comes to reporting, looking at accuracy versus F1. And there's no NA. This is a very clean data set. I will get rid of the user ID because it doesn't have any explanatory power. And then there are some is this that one? No. Okay. So dealing with categoricals. So if your categorical variable, guys, this is important for decision tree because if you pass these strings to the model, it's going to complain. Right? So male versus female, it doesn't understand. You don't need to make them dummy variable. However, you have to make sure that you use some numbers. And whatever number, it really doesn't matter. You define it male as equal to 100, female 200. It really doesn't matter. Here, for the sake of argument, we do 1 versus 0, right? So I'm going to say if gender is male, call it 1, otherwise 0. Just you can call them anything. It doesn't have any impact. We are not calculating distances, remember. And then, so these are data visualization. I think we can go through these ones very quickly. And basically, these are the correlations between the variables. And then we can look at the pair plot. And I like to see it by different target variables, purchase or not purchase. And because there's a clear distinction between the distribution, I hope that I can get a good model out of it, right? Because I like what I'm seeing here. All right. And usually in real world, the data is not this clean. The data set that I chose for the lecture classes usually are the one that I wanted to make sure I deliver the message, but in real world, you're going to have hard time picking up which model is working best, right? Like your next homework, you're going to see in the homework is not going to be that, well, it's not that clean. Okay, so let's go ahead and train the model. Scaling the features, should I need to be worried about scaling the features? Absolutely not. This is decision tree. So all good. The model, the function that we're gonna, the class that we're gonna use is decision tree classifier. It comes from scikit-learn tree. This is a class tree, and then this is a set of functions from that class. Now I'm going to call my classifier tree_classifier, and I pass the default values as inputs, right? So the default values for decision tree classifiers are all these things. So the criterion is going to be Gini, splitter, best. Max depth, there's no max depth. Minimum sample split. So this is minimum number of observations in each split. By default, it's 2. It's very small, but we will see. Minimum sample leaf. So this is the minimum observations in the terminal node. And minimum weight fraction leaf. Again, we're not going to deal with class weight in this one. So for random forest, I'm going to explain more. Maximum features. Random state is there. Well, the model has itself a random state. You can put a random state here. Well, we can set a random. If you want to see the same results as what we see here, you can put a random state. Minimum impurity decrease. This is one of the hyperparameters we talked about. And then the minimum impurity split. Again, we want to see at least this is a number of minimum impurity that we required. This is our alpha, CCP alpha. A cost complexity pruning alpha. Okay, we're going to play around with this one. Okay, instead of guessing all these numbers, by the way, you can do grid search and look for the best combination, but because we have lots of variables, it's going to be super costly if you do grid search. So this cost complexity pruning is going to do all these things for us. Because if I increase alpha automatically is going to shrink the tree. So it's as if I, for example, put the max depth is equal to 3 or 4 or whatever. Right? So that's the plan. So we start with the default values though. So the default inputs, we train the model, and decision trees are fast when it comes to training. Well, depending on the dimensionality of the data. And we make some predictions, right? So these are the predictions in the test set. Then for this one, I'm not going to make it customized classification reports, we're going to use the scikit-learn functions directly. So confusion matrix, well, not bad, 42.6. This is false, positive, false, negative. And then built-in classification report. Let's look at the classification report. So what is my accuracy? 76%. What is my F1 score for the default? This is for the purchase one, 67%. All good. You know, what I'm saying here is not that bad, right? If these numbers are close to 50%, you should be concerned because it's worse than flipping a coin. Okay. All right. Now, so this is the initial output of the decision tree, but using the default inputs, right? Let's optimize it. Let's prune this. This is the bushiest trees that we can think of right now. Let's start pruning it back. So I'm going to choose alpha using cross-validation. So this is both decision tree classifier and decision trees regressor have this method called cost complexity pruning path. So what you pass to this method is the train set X and Y, right? The output is going to be something interesting. The outputs are two things, actually. It gives you a bunch of alphas. So this is called CCP alpha, bunch of alphas, along with a bunch of impurities, right? So automatically, it's not going to try, for example, alpha is equal to 0 and then 0.1, 0.2, 0.3. It's going to be optimized, choosing different alphas, right? So you have, let's say you have a bunch of alphas and then a bunch of impurities. So what's our job here? Our job is to pick these alphas and calculate using cross-validation, calculate the accuracy of the model using each specific alpha and plot them together and pick the one that gives me the best accuracy. Is that clear? So this is what we do. So I'm. How does it pick the alphas? Like, how does it? Not how does it create the arrays, but how does it decide which alphas to put into the array? Well, I see. So, for example, why the next one is not this one? So that's so. For example, why is 0015? Why the next one is not 0016? Is that what you mean?
No. Just like why? Like, is there a certain way that it's choosing those random numbers, or?
Oh, these are not random.
Oh, okay.
Yeah. So the cost complexity pruning. Again, you can read the documentation for it, but that's beyond the scope of the class. Yeah.
Oh,
Yeah.
okay.
It's optimized.
Okay.
The first value may be optimized, but random, but it's optimized. The steps are optimized and everything. It's related to the number of terminal nodes you have. There are lots of things, okay, but one of them is number. So if I can, so if this is something like this, I can guess that maybe the tree is not super bushy, but sometimes when the tree is super bushy, I get lots of more alphas because there are some convergence criteria behind the scene that the algorithm is picking. So it's not always 10 numbers. Sometimes it's 100 numbers. Okay. Very good question. Yeah, I think actually I'll put a link. It's not there yet, but I'll put a link here to navigate you to if you want to know more behind the cost complexity pruning. There are lots of variation of that. Okay. Okay. So again, I'm gonna save these alphas. I call it CCP alphas, and guys, remember I call this object path. If I do path.ccp alphas because it has two. This is a dictionary, right? The key 1, key 2. So I'm going to extract the key in this alphas. Now I'm going to work with cross-validation, right? Remember, at the end of the day, we want to do cross-validation. And I'm going to write a for loop and search within all those alphas, right? These are the alphas that we got from that CCP method. And I calculate accuracy for each single alpha. We have done this before, so this is nothing new. So I calculate the accuracy for them and then plot them. Let's plot them. So this is what it looks like, right? And obviously there's at some alpha level, the accuracy is maximum. This is what we're looking for. Are we good? Do not trust your eyes because sometimes this line is kind of flat in your homework. This is what you're going to see. Just use argmin, argmax function. This is accuracy. We're going to do argmax. I say, okay, what is the maximum? When does the maximum happen in our output table? Remember, the output table is this. I want to say that where does the maximum happen? What is the index number? Maximum accuracy happens at index number 16. So here 17 because it's random. It has a random random state involved. So that's why I get a different number. So 17 means that start from 0, right? So it means that, so for example, if it is 17, in the real data, it's 16 observation, right? So sorry, 17th observation means that we have, so for example, this is 17th observation, but the index number is 4. So 17th observation, the index number is 16, right? Okay. And then we can look at, actually, we can use iLock to basically says that take this 17 and give me back what are the values in the output table for that 17th row, right? Says that, okay, the alpha is 0081 and the accuracy is 89%, right? Did we improve the accuracy? The original version, it was 76, and we improved it a ton, right? We went from 76 to 89, which is fantastic, right? Okay, so then we're gonna refit the entire thing. I'm gonna save this optimal alpha, call it optimal alpha, and I'm gonna refit the entire thing using that optimal alpha. Okay, and we can look at the confusion matrix again. You see how it improved, right? We can look at these numbers, they are gonna improve. Well, 94, 91, this is really good. Accuracy is 93 now. We can estimate this number by doing cross-validation. So let's do that. So the estimated number for 93% is 88. And then finally, we can visualize a tree. So let's go ahead and visualize a tree. There are 4 different ways to visualize, at least 4 different ways to visualize a tree in Python, right? So I put a link here for you. The best one is using ggvisor? No, not GG. What was it? But that's heavy. So we're going to use this. This is something that the scikit-learn recently added, plot tree. The previous time that I was teaching, it wasn't there. So last time we used GraphViz. But the problem with GraphViz is that it's super heavy. Okay, it's a super heavy package. And then, so for this course, I want you to work with this plot tree. In terms of graph, it's not as beautiful as GraphViz, but it does the job for us, right? So we're gonna use plot tree from the scikit-learn package. But before doing that, I want to show you something. So if I go ahead and look at the data, age versus estimated salary, and color coded based on purchase or not purchase, right? See how beautifully separable the data is already? So I should not be super happy with, not happy, super surprised with this high accuracy, 93%, because the data was so cooperative if I want to use a decision tree, okay? Then, okay, so this is how we can visualize a tree. So I'm gonna make a new classifier, call it D3. I say the maximum depth is 2 and alpha is 0. When alpha is 0, I say that, okay, extend the tree as long as you meet the stopping criteria. Here is, let's say, we want to visualize a tree with the maximum depth of 2, right? And let's look at the X-train. So this is how we plot the, well, we don't need this contextual help anymore. This is our tree. Guys, remember, if you want to make a split, what is your best split? Most probably you're going to start with age, and then the next split is something like this, right? So age is around 40-ish, 41, and the estimated salary should be around 90, right? Let's see how did we get that. So age around 40 and salary 90. Does that make sense? So the algorithm is doing the good job. And why did we stop here? Only depth is 2, because we manually wanted the model to do that. Depth is equal to 2, right? If I say depth is equal to 10, let's look at the tree. Well, it's going to be a lot more bushier, right? And so this is the maximum depth of 10, right? But does that mean that I have 2 to the power of 10 terminal nodes? No, because look at that, some of them, the tree is going to stop here because the number of samples in that terminal nodes is small. Then what else do we have? So for example, let's go back to the tree of 2. Let's look at the numbers, because this is something that I want you to interpret for the homework. So what do we have? We have Gini, we have samples, we have value. Look at that. We have 320 observations, right? So 300, we start from 320. Next, left split, right split, let's call it left and right. So 231, 89, if you add them up. And out of, so in the test set, 209 of them did not purchase the vehicle, 111 did purchase the vehicle. And we're going to make further split like this. Out of these 209, 194 here, 15 here. Are you following the breakdown along the tree? I think it's pretty straightforward. What I want you to pay attention that the Gini should decrease as you go down the tree, right? Why? Because you hope that you get a more pure classes. If the Gini is close to 0.5, it's completely random, right? The distribution is uniform. Now I get a better Gini. Okay, good news. I get a better Gini. This is a very good class, right? This is completely random. This is not necessarily bad. What is this very good class? Look at that. They're here. Right? This is where the Gini was super close, super small. Okay. And then guys, remember, again, the caveats of this simple tree plots that comes with scikit-learn is that it's not beautiful, and it's not, for example, it doesn't even have yes or no on the trees. So just remember, when you go to the left, this is true, this is false. Just remember that, true, false. If you're into these kind of things, you can do GraphViz, install GraphViz, but just make sure that you follow documentation for installing the GraphViz. It's a little heavy. If you're on your laptop, I don't recommend it. With a low RAM, I don't recommend doing that. Okay, you can save this. I think you have seen the figure on. You can save it as a PDF or PNG or whatever, and add it to your report. So let's look at these questions. What is the level? So what is the level here, guys? 2, right? So I have 1, 2. What is the number of terminal node? Can somebody answer this question? What is the number of terminal node? 4, right? The max terminal node is 4, just be aware, right? And how do you make sure that each terminal node has at least 50 observations? Look at that. So this terminal node has 195, this 36, this 26. Maybe you say that I don't like this kind of estimation, this is too small. How can you make sure that each terminal node has more than 50 observations? What should I do? I should go back to the tree and change one of those tuning hyperparameters, right? Let's add it. So minimum, as soon as you start typing minimum, you get something like this. So minimum sample leaf. This is what I'm looking for, right? Minimum observations in the leaf or terminal node. So if I put it 50, I want you to pay attention to the tree. Let's see what happens. So these, I should get rid of these two, right? It will be replaced by something else. You see, the tree doesn't continue further because if we want to split the 89, it will be less than 50. And then, yeah, this is right 50 and 181. Are we good? Okay. I changed the one of the hyperparameters, minimum sample leaf. Oh yeah, the Gini changes, right? Yeah, every single time. Remember, this algorithm has some random state involved, but it will change. Yeah, this split is really good one. We're not surprised. We are here. Okay. All right. Then finally, let's do some advanced visualization. I'm going to do the classification only. We are going to leave the regression. I'll first leave it as exercise, but next class I'm going to review it quickly. We'll see. So for the advanced visualization, this is something that we have done in our previous models as well, but this is a fun part. So I'm going to stick to the 2-dimension data. Let's look at age versus estimated salary. And this is really cool. We're going to start with a tree that the max depth is 2, right? Let's visualize a train set. This is look at this beautiful decision boundary in the train set. If I change this max depth to 1, what do you expect to see before seeing the output? Just a straight line. Very good. Most probably it's going to on age, right? So let's see if we can get that. Awesome, right? If let's max depth to 100. What do you expect to see? I'm making a very bushy tree. Yeah, it's going to be very bushy. Very overfitting, right? Let's look at that funny thing. Look at that. It's absolutely overfitting, right? Now, if I apply the same data, same model to the test set, these are very poor predictions, right? Let's see if you're lucky if you get an observation in the test set here, but I really doubt. So let's say do that. Look at that. These are absolutely wrong regions for the predictions. Do you see that? Okay. So that's it. And if, again, this is very overfitted model. So for that reason, the confusion matrix is not that good. But if I don't know, if we stick to that easy number 2, I think in the test that we get a very good numbers. Yeah, right. So this is doing a really good job even in the test set, on the test. Okay, are we good? Can you bear with me 5 more minutes? Well, we have 10 minutes officially, but I may go over time by a couple of minutes. Just bear with me because it's easier if you can do it this class. Okay, we're done with the classification. For the regression, we are going to work with, actually, I'm not going to run the code, so I'll just read through it. We're going to work with the wage data set. This data set we are completely familiar with. We are trying to predict the wage versus hours, education, IQ, experience, and etc. Right? This is an example that I want to show you that not necessarily decision trees are going to do a good job when it comes to regression. Okay, let's see why. So data preprocessing, we're familiar with all these things. So then make sure that we don't need to scale the parameters. There is no dummy variable that comes as this character. So I don't need to be worried about those one either, because merit is 0, 0, 1, black is 0, 1. So I don't need to change them. And then let's run the regression. So here it is. So when it comes to inputs of the model, so these are the inputs of the model, the decision tree. Look at that. The only difference is that we're importing from the sklearn tree, decision tree regressor. The previous one was classifier. This one is regressor. So what are the inputs? Well, actually, I have to run this one. Otherwise, it doesn't. Okay, so what are the inputs? Again, we have criteria. It is MSE. Why? Because this is regression. In classification, do you remember it was Gini versus entropy? So here is MSE, splitter, max step, the same story. Max step, minimum sample split, minimum sample leaf, and then minimum purity. What else do we have? CCP alpha, the same story, right? So then I go down the notebook. Let's evaluate the initial model with default inputs. So the initial model is doing something like this, and this is doing a poor job, right? And actually, this is a conceptual question. Why do you think I have many different values for y? Guys, remember that the circles, the dots are predictions. And as you can see, I have many of these predictions. So what does it imply? Remember, in decision trees, the predictions are y bar in each region. If I have 3 regions, I should have 3 numbers, 3 simple numbers. But why do I have lots of these ones? So what do you infer? Okay. So no, it's not necessarily a great job. Is it a small tree or very bushy tree? Very bushy tree, right? Let's have fun and see this one. So this is the very bushy tree. If I go ahead, if I go back and change the max depth is equal to 1, what will happen? Very good. It's going to be a horizontal line. What is that line? No, it's going to be horizontal because we are plotting the y hat versus y. Oh, it depends where you put the y hat. I get it. Yeah. So what is this number? Look at that. Well, when the depth is 1, we can have 2 regions, right? 1 split, 2 regions. So what are these numbers? These are the average in those regions. Okay. All right. So let's go back and remove this default. So this is a super bushy tree, right? I have lots of. And the RMSE is large. Well, how do I know that it's large? Because if you remember, we did the same data, we applied the same data set to the KNN. So now let's go ahead and prune this bushy tree back. So we're going to use exactly the same method, right? So cross-validation for decision tree regressor, there's cost complexity pruning path. So, and then I save these alphas, make a cross-validation RMSE, and then in each tree, I make sure that I'm changing the alpha. So for each alpha, I'm calculating the RMSE, and then I'm plotting RMSE versus alpha. What is the optimal value of alpha here, right? The minimum, because we're minimizing the RMSE. For accuracy, we were maximizing the accuracy. For RMSE, we're minimizing the RMSE. So the optimum alpha is going to be around, what's the number? 4.6, well, 0.46, because it's multiplied to 10 to the power of 10. Okay, so here's a good one. Look at these alphas. These are huge. 10 million, 1.2, 12 million, and etc. Right? So the reason is that, what is the objective function? Minimizing the RSS, residual sum of squares, right? And what is the wage? Wage is in $1,000, and these are CEOs. So wages are $1 million, $100,000. If I square them, that's why the RSS is super large. In order to make sure that the R square is going to be squeezed down, the alpha should be super large. Does that make sense? Hopefully, okay. Just rewatch this part of the video, but I hope that it makes sense. So don't think that the alpha is always less than 1, greater than 1. That in classification, yes, but in regression, it depends on the unit of your target variable. If I change the weight to log weight, this alpha should be around 10, 20, something like that. Okay. We go ahead and do exactly the same process. We find the optimal value of alpha and then refit the model. We get the RMSE. Did our RMSE improved? The answer is absolutely yes. We went from $516,000. How do I know that it's dollar? Because it's RMSE and the target variable is wage. To $390 something dollars, right? And if you do the simple linear regression model, it's 370 something. So the decision trees is doing a lot worse than a simple linear regression model. Okay. We can visualize the tree. Let's visualize the tree with the optimal alpha because it's penalizing a lot. So if I use the optimal alpha, it seems that the path is 2. The maximum level is 2. Right? Look at that. So here I'm not imposing max depth is equal to 2, but I'm imposing alpha. This alpha was large enough to make sure that the max depth is 2. You following? Okay. Then, yeah. So why do you think that decision tree did not a good job? Look at this one. Is it, do you think, is it a separable data set? Can you find a nice cutoff? No. So that's why the decision tree was not able to do a good job. Okay. Yeah. And then if you want to see the regression line, again, this is absolutely, you're not going to see this in practice unless you're working with the data set with only one feature, which is very, very improbable. But if you want to do that, we can. Let's say the max depth is 2. If you want to visualize it, at most, I can have 4 Y bars. 1, 2, 3, 4, right? If I change the max depth to 6, well, I cannot because I haven't run it. So this is going to be a lot more jiggly. Does that make sense? Okay, we're almost done. Okay, so just send me an email or the TAs if any part of this was not clear. But at this point, I'm quite confident that you can handle it. You know, code-wise, that was nothing complicated. Just focus on the new parts and get the big picture and get the concept, get the intuition. What I want you to take away is that get the intuition. All these things eventually is going to be automized. It's automatically is going to be done. So your job is to understand what's happening behind the scene. All right, so let me go ahead and stop the recording. And if there's no question, good luck with the homework during the weekend and see you on Monday.